Hello, Vital Sign. Today we're going to talk about Rook's graphs. An n by k Rook's graph is a specific type of graph whose vertices represent squares on an n by k chessboard, and whose edges represent all possible legal moves of a rook on that chessboard. In other words, the connections between two vertices in a rook graph represent a legal move for a rook to move from one square to another square on the chessboard. For those that don't know, a rook can move anywhere along its column or row on the chessboard. Our 8x8 Rook's graph corresponds to the 8x8 chessboard and every possible legal move on that board. While we could define a rook graph solely with the chess-related definition of the legal moves of a rook, an n by k Rook's graph is also the Cartesian product of the complete undirected graph on n vertices and the complete undirected graph on k vertices. Recall that a complete undirected graph is one in which every vertex in the graph is connected to every other vertex in the graph. The graph shown is a complete graph with 4 vertices. I suggest you check out my video on the Cartesian product of graphs if you haven't already for background information on the graph operations that follow. The Rook's graph with 64 vertices corresponds to the conventional chessboard of 64 squares, and is the Cartesian product of 2 complete graphs on 8 vertices. What I would like to do first is show you the intuition behind why the product of 2 complete graphs on 8 vertices gives us a graph with edges that capture the rook's legal moves on a chessboard. Picture a chessboard where we label the rows with numbers 1 through 8, and we label the columns with letters A through H. If our rook is stationed at A1, then it can move to A2, A3, and so on, through A8. Or it can move to B1, C1, and so on, through H1. That means for a rook graph, where each chessboard square is represented by a vertex, the vertex representing square A1 should have connections to those representing squares A2 through A8, and B1 through H1. In other words, if a rook graph is to capture the structure of the legal moves of a rook on a chessboard, any vertex defined by an ordered pair of its column letter and row number must connect to all other vertices in the same column and all other vertices with the same row number. Doesn't this definition of an ordered pair remind you of Cartesian products of graphs, where each vertex represents an ordered pair of vertices from each factor graph? Now, think of the Cartesian product of 2 complete graphs on 8 vertices, one labeled with letters A through H, and one labeled with numbers 1 through 8. As we learned, the Cartesian product of these 2 graphs will have 64 vertices, each corresponding to an ordered pair of vertices from each graph of the complete graphs. According to the first adjacency condition for the Cartesian product of graphs, 2 vertices in the Cartesian product are connected if their first entry in the ordered pair, in this case their letter, is the same vertex in the first graph, and their right entries in their ordered pair, in this case their number, are adjacent vertices in the second graph. In this case, all numbers, or all vertices in the second graph, are adjacent, which means that all Cartesian product vertices with the same letter and different number will connect to each other. What we get is that each column is a complete graph on 8 vertices, as every vertex in the column is connected to every other vertex in the column. This is precisely the property we're looking for in a rook graph, where all vertices within the column should connect to each other. According to the second adjacency condition for Cartesian products of graphs, 2 vertices in the Cartesian product are connected if their second entry in the ordered pair, or in this case their number, represents the same vertex in the second graph, and their left entries in the ordered pair, in this case their letter, are adjacent vertices in the first graph. In this case, all letters or vertices in the first graph are adjacent, which means that all Cartesian product vertices with the same number and different letter will connect to each other. This means that each row is also a complete graph on 8 vertices. This is exactly the property of a rook's legal moves, where a rook can travel to any square in its row from any square within that row, and any square in its column from any square in that column. Let me show you what the full Cartesian product looks like, as it's way too many edges for us to draw out ourselves. Isn't it amazing that just from the adjacency rules and properties of the Cartesian product of graphs and the adjacencies of complete graphs, we are able to capture the properties of the legal moves for a rook on a chessboard? To finish the video, I'd like to talk about some properties of Rook's graphs. For one, each vertex can reach every other vertex in 2 steps, meaning that Rook's graphs have a diameter of 2. This is because each row and column is a complete graph. So starting from any vertex, we can move into any column or row in 1 step, and thus any vertex on the board in 2 steps. The number of edges, or the size of an n by k Rook's graph, is given by the formula in the upper right-hand corner. This formula can be found in a few ways, but one is to realize that the Rook's graph is really a collection of n times k different complete graphs, one for each column and row. If there are n columns and k rows in our graph, and remembering that each column and row is a complete graph, then we have n complete graphs with k vertices and k complete graphs with n vertices in our graph. Also notice that the edge sets of the n times k complete graphs are disjoint, meaning there is no overlap between the edges in each complete graph, as a single edge cannot correspond to both a rook's move along a column and along a row. Since the edge sets are disjoint, we can find the size or number of edges in a rook's graph by counting up the edges or sizes of each complete graph. If you recall, the size of a complete graph of some number of vertices x is x times x minus 1 divided by 2. And remember that we have k complete graphs with n vertices and n complete graphs with k vertices. That gives us this expression for the size of our Rook's graph. The expression simplifies to our formula in the upper right-hand corner. In my next video, we're going to cover tensor products of graphs, and in future videos we'll cover strong products and king's graphs, a type of graph that captures the legal moves of a king on a chessboard. Thanks for watching. Please subscribe, like, share, and comment. Have a great day.